In chapter 12, we're going to look at three different analyses or models, one in each section. The first one is equality of population proportions when you have more than two populations. In chapter 10, we looked at population proportions for two populations. Now, what if we have three or more populations and you want to test whether the population proportions are all the same or are they different? Then extension of that is the independence of two different variables. And third section, the third topic is goodness of fit. If you have a discrete probability distribution and you have a sample, and see whether the population from which the sample is taken is same as the discrete probability distribution we are assuming. And we'll also look at normal probability distribution. Now, one commonality among all of these three different sections is in each of them we will be using the chi-squared test. We introduced chi-squared in chapter 11, so we're going to use the chi-squared distribution in each of these three different sections. So let's first take the multiple population proportions. So three or more populations. So we have, say for example, k populations. In each population we have a population proportion of what we define as success or yes and no. And we want to test whether all the population proportions are equal as against the opposite, the alternative hypothesis that not all of them are equal. So these are the only type, unlike chapter 9, 10 and 11. Here we do not have the three different types of hypothesis. We have only one type, and that is all the population proportions are equal. The opposite of that is at least one is different, or you can say that not all population proportions are the same. So this is the only type of hypothesis, and therefore this is a one-tailed test. So it's always one-tailed test. There is no two-tailed test here. It's always one-tailed test. Now we take samples from the k different populations. Okay, each will have a sample size, and the sample will be divided into number of favorables and not favorables, or S answers and no answers for each of them. So now you can sum row wise, and that will give you the total S's from all the populations and total no's. So that's your row total. And if you sum these individual if you sum the columns, you get the sample size for each population. And if you sum all these sample sizes from each population, so we get the total sample size. So total sample size is the sum of these column totals. So once we have this, then we can develop the expected frequencies if the null hypothesis is true. So if the proportions for population 1, 2, 3 up to k, if they are all the same, population proportion of S's, if they are all the same, then what is the expected number of S and the expected number of no's you will see for each population, and that's given by this formula. So you take the row total, multiply by the column total, and divide by the total sample size. So that will give you the expected frequencies for each row and each column. Then we can compute a chi-squared calculated value by taking the observed value minus the expected value and square that and divided by the expected value. And the degrees of freedom is k minus 1, k population minus 1. Now this chi-squared value, okay, if the expected frequencies and the observed frequencies are very close, so that means null hypothesis is probably true, then the chi-squared calculated value will be really small. The more the null hypothesis is not true, the larger will be the difference between the observed and expected frequencies, and therefore the larger will be the value of the chi-squared calculated value. So the test statistic, if it is large, then you reject the null hypothesis. If it is not large, you don't reject the null hypothesis. So it's always a one-tailed test to the right. So all we need is a critical value for the chi-squared. So critical value, the table value is given by chi-sq.inv.rt, and alpha, not alpha over 2 but alpha, and degrees of freedom is k minus 1. Now if the chi-squared calculated value is greater than the chi-squared table value, then we reject, otherwise we cannot reject. Now of course the chi-squared table value you can also get the chi-squared table value directly from the table from the back of the book, and I have a video on that. But you don't have to use the table from the textbook. You can always use the Excel sheet and type in this function and get the chi-squared table value from Excel also. You can also do the test using p-value. The p-value is given by chi-squared dot dist dot rt. Again, it is only the right hand side tail, and we have seen this formula before. Now if you reject the null hypothesis, then a question arises, which of these proportions is actually different from the others? Okay, we know that at least one is different. Now which one is different? And for that we're going to do, we can do tests for each pair. So if you have k population proportions, then k taken 2 at a time, so there will be k times k minus 1 over 2 number of pairs. So if you have 3 p's, then you will have 3 pairs, p sub 1, p sub 2, p sub 1, p sub 3, and p sub 2, p sub 3. Now if you have 4 populations, then you will have 6 pairs. So p sub 1 with 2, 3, and 4, so that's 3 of them, and then p sub 2 with the other 2, so that's 3 plus 2, 5, and then 3 and 4 is 6. So there are 6 possible pairs. Okay. Now for each pair we have to compute a critical value CV, okay, and you use this formula to compute the critical value. And if the absolute value of the difference in the sample proportions, if it is greater than the critical value CV for that pair, then we say, okay, that difference is significant. Otherwise that difference is not significant. So now let's look at an Excel example of all of this.